Dear all, I am going to take the machine instruction and programs in the topic queues, subroutines, additional instructions. Then, in case of input-output organization, the subtopics are accessing I/O devices, interrupts, direct memory access, buses, interface circuits, and standard I/O interface. So in this case, normally queues are aligned with the stack only, but there are some difference between the stacks and queues. In case of queues, uh, we can handle the data from the top of the queue as well as from the bottom of the queue. So one end of the stack, I mean that bottom of the stack is fixed. So we cannot move the data to and from the bottom of the stack. But in case of queues, two ends, from the two ends we can take the data. We can handle the data. So while the other end rises and falls as data are pushed and popped in case of queues. But in case of stack, from the top only we can take the data, bottom is fixed. So in case of stack, there is only one pointer is enough to indicate the stack location, I mean the location where the last data is stored. But in queue, both ends move to higher addresses as data are added at the back and removed from the front. So in the front, the data can be removed, but from the bottom, the data can be added. This is what the procedure. Alternate is not possible. So two pointers are needed to keep track of the location of the queue. Another difference is a queue would move through the memory of computer in the direction of higher addresses only. But in stack, while we are popping, the address will be increasing. So while we are putting the data, the address will be decreasing. But it is not the case in queue. Only higher order address will be possible when we are moving the data in and out from the queue. In a given program, next topic is subroutine. So subroutine, already we know that the stack, what for we are using stack for the usage of subroutine, while the control complete the execution of the subroutine, it has to turn back to the main program. For that, the address of the instruction should be known, and this address will be stored in the stack. So the control will take over the address and then coming back to the main program. This is what the concept. So in this case, in a given program, so now what about subroutine? So okay, stack purpose is to manage the subroutine function. Okay, but now what is subroutine? In a program, there are some a small intermediate task. In that task, for example, sorting out the numbers, either increasing order or decreasing order. And another example, suppose for a given number, you find out the sine function, sine of that particular value or cosine of that particular value. So in that way, we can perform a smaller amount of task by using various numbers, and at the same time the same task will occur in the main program in so many places. So n number of times the same task will be executed. For that, n number of times the same coding is written in the main program. What is the use? What is the disadvantage? It occupies more and more space. That is why in, in terms of a subroutine, one function will be written and stored in the memory, but separately, not in the main program. That memory location address for that subroutine will be different. It will be stored somewhere else, and that task is subroutine. And after completing the subroutine steps, finally it should go to the main program. And how it knows that the subroutine task is yet to be completed? It will be indicated by a code, namely RET, that is return function, return command. After facing the return command, the control automatically goes to the main program and continues from there. This is what the subroutine. Okay, so simply we can say the subtask is called as subroutine. See, it is often necessary to perform a particular subtask many times in different places for different data. That task is known as, that subtask is known as subroutine. For example, as I have told you already, that it may be a sign function or sorting the values in the increasing order or decreasing order, and then it is possible to include a block of instruction that constitute a subroutine at every place. We can write that same subroutine in the main program wherever it is necessary. But what is the drawback? It will not save the space. It needs more space where it is needed in the program, but it saves the space only one copy of the instruction, because the task is doing the same function only. So why do we use many times at one place separately? We can use whenever it is necessary. We can, the control can go to that place and can perform. So this is what stated here. To save space, only one copy of the instruction that constitute the subroutine is placed in the memory. And any program that requires the use of subroutine simply branches to its starting location. So what is the meaning branches? It is not continuous address. It is separate address. So definitely the control has to transfer. It has to stop the main program execution, and it goes to the some other memory location. That is why it is branching. It is known as branching. When a program branches to a subroutine, we say that it is calling subroutine, because a subroutine is called in the program, in the main program. The instruction that performs this operation is named as a call instruction. Okay. Next one. After a subroutine has been executed, the calling program must resume the execution. So wherever it departed, in that place it has to go back, continuing immediately after the instruction that call the subroutine. Where the branch occurs, from the next sequence onwards, it has to continue. The subroutine is set to return to the main program that called it by executing a return instruction, RET. Return instruction, it is RET instruction. Since the subroutine may be called from different places in the calling program, provision must be made for returning to the appropriate location. So it has to come back wherever the transfer occurs. For that, a provision is provided. That provision, what is that? I will tell you later. The location where the calling program resumes execution is the location pointed out by the abbreviation of PC. So, what is the main function performed by program counter? So, program counter is nothing but it is a register only. It stores the data, and what content the program counter is having, that is nothing but the address of the next instruction. So, suppose for example branch occurs at 2002, address of the next instruction is 2003, that 2003 will be held in. Once if it comes to 2002, it is under execution. Immediately address of the next instruction 2003 will be stored in program counter while the call instruction is being executed. So that the previous instruction is going on for execution. Hence, the content of program counter must be saved by the call instruction to enable correct return to the calling program. So, before going to the subroutine address, the program counter content will be saved. Then only after experiencing RET instruction, the control will take the uh, take the address of the next instruction and then goes to the uh, goes to the particular memory location. So in this example, I have already told you that 2002 branch occurred. So 2003 will be stored, and that 2003, that means it is equal to the content of the program counter is taken away by the call instruction, and then it goes to the particular memory and the concerned memory location from where the program resumes to the execution. Next one, the way in which a computer makes it possible to call and return from subroutine is referred to as subroutine linkage method. Now, that the content of the program counter 2003 will be taken away, I told, but where it is stored. So, without any hold, that 2003 cannot be taken away from the call instruction. So now one more register is to be stored. What is the name of that register is subroutine linkage method, that is link register. This link register is storing the content of the program counter address of the next instruction. So in this example 2003 is stored in the link register. So after saying return instruction, the control the control goes to the link register and takes the address of the next instruction and go to the main program. From 2003 onwards, it takes the execution. So, in conclusion, the summary of this topic is call instruction is just a special branch instruction. So, branching where it is going to subroutine. So, number one, store the content of program counter in the link register, because it is after non-living thing, it will forget from where it went away. So that address will not remember. So for going back, this address is stored in the link register. And second one, branch to the target address. So in the instruction itself, subroutine means subroutine address. If it is stored in 4003, 4000 jump to 4003, it will be written in the main statement. So target address as seen from the main instruction, the branch will occur. And the return instruction is a special branch instruction which is given in the last of the subroutine that performs the operation, and branch to the address contained in the link register. And next one, so whatever I have explained is diagrammatically given here. So the memory location is continuously moving on 200, 204, 201, 2, 3. So in suppose 4, normally stack means 1, 2, 3, 4, 4, 0 to 3, 4 to 7 in that way, 4 bits. Already I told you that. That is why the address will not change from 200 to 201. It will step with 3. So 200 plus 200, 201, 2, 3. So after that 204 because 4 bits. So 200, 204. So in 200, it is calling the subroutine call sub. So the subroutine name is sub here. So we can give any name to the subroutine. So it goes to the sub. Sub is stored in the 1000th memory location. So first instruction and then going on, and finally it is facing the return instruction. So after seeing RET instruction, it comes back to the 2004, which is the next instruction, and 2004 is stored in the link register as well as in the program counter. The next one, actually it is programming, machine instructions and programming. That is why the topic comes out with the arithmetic operations. So additional instructions, like I subtitle additional instructions, load and store. So what is load and store? It is read and write only. Load and store instructions can be replaced by, in the coding, it is given as move. It is given as move. So load and store are nothing but the move only. They can be replaced by another instruction move. So increment and the decrement instructions can be replaced by. So increment means automatically it is add instruction. Decrement means it is default subtraction subtract respectively. So clear can be, so clear, if you give clear instruction, it is giving 0 only. Okay, so this clear instruction may be replaced by move 0 wherever you want to 0. I mean, if you are initiating the arithmetic logic operation, then you have to start with the 0. So that 0 will be given by clear. Otherwise, add 0. You can use the add instruction also. So clear can be replaced by moving instruction, moving or copying 0. 0 instruction containing an immediate operand of 0. So first one, there are so many types of this additional instructions. Number one, logic instructions and or not, basic only. So basic instructions are there here. Now for example, not DST means a destination. So wherever you want, that is DST, destination address you have to give. So here DST given, DST means a DST address. Not means opposite. So 0, not 0, 1, not 1, 0. So in this manner, this expression will perform. And next one, complement. It is also equivalent to not. So you can say complement or otherwise not. So complement means you can use the negative numbers. Complement all bits in the destination operand. So what is the meaning? Plus 3 is converted into minus 3. It is the complement. So reverse. Plus means minus, minus means plus. Okay. So plus means no need to put anything. What is the equivalent of 3? 1, 1. So it is 4 bit. Already I have told you that in the computer architecture is designed in such a way that in one address of 4 bits. So 0, 0, 1, 1 is converted into minus 3. So in digital electronics, minus number, how you will get? We have to take the ones complement. So ones complement means all zeros are changed to 1, all ones are changed to 0. This is the ones complement. For indicating the negative number, mentioning the negative number, we have to add LSB with 1 to the ones complement, so that we are getting 2's complement. 2's complement is nothing but negative of the number. So here 3 we are giving. So complement of 0011 is 111100. It is the complement of this one 0011. It is one's complement. So for two's complement you have to add with 1 in LSB. So finally you will get 1101, and this is equal to -3. So that is what here given, -31101. If 3 now we are using the registers. So anyway, storage, we are talking about the storage, memory storage registers also. So this number is stored in, suppose in the program we have to write where it is held. So the 3 is is stored in R0. This is the instruction. So how to write not R0? So suppose R0 here, R0, the content of R0 is 3. 3 means plus 3. This not R0 means not plus 3. So it is the result is -3. We should get -3. Otherwise it is only one statement, only one command. Not R0 means not plus 3. So -3 we will get. But some other way also we can do. How? Add hash symbol means immediate value 1 comma R0. So in here R0 is having 3, is having 3, and then active -1. So not R0 means R0 is storing 3, it's having 3. So not R0 means you will get to 1100. So 0011 is becoming 1100, and then add immediately 1 to R0. Now this R0 contains 1100. So add 1 means you have to add in the LSB, so that you will get to 1101. So not R1 can be written as not plus 3. Not plus 3 can be written as not R0, and then add to the content of R0. Finally, you will get -3. So negate R0 also gives -3. So not or negate you can use. The next one, next B, other instruction, shift and rotate, circular shift. So rotation means circular shift. Other name given to the rotation is circular shift. So it is ordinary shift, it is rotational instruction. First one, shift left. So shift means you can shift left or you can shift right. Both are possible. And in this case also logical and arithmetic also there. So first one, logical shift. Logical shift left. It is useful. Then before that we have to know why do we perform this shift operation or rotating operation. We need to know the application where we are using. We need to know. So it is useful in, so simply we are not doing any operation. Application only we are doing. So logical operation, this shift is used in multiplication by powers of 2, which is helping in bit manipulation, tracking overflow, data encryption, checksum calculations. So for these many applications we find for shift operations. So for example, here #3 why we have taken means 3 times we have to shift. 3 times. 3 positions we have to shift. That is what the meaning as symbol 3. Now, for example, 1 0 1 1 0 1 0 1. This is the input values given, and we have to shift the position number position by 3. So here it is left. So left shift means MSB. In the MSB we have to take 3 because 3 bit position we need. So I have given to view the numbers clearly. I have given the colors 1 0 1. So 3 bits after third bit, fourth bit onwards you have to shift left. It is left. So 1 1 0 0, and this 1 1 0 0, and this 1 1. So three bits we have to shift means those 3 bits are discarded, and finally it is 0 0 0 because it is 8-bit number, so that these 3 are replaced with 0 0. So almost these 3 bits are discarded. It is waste only. So 3-bit shift means either right or left shift. We have to discard the how many discard by the number of shifts we perform. 3 shift means 3 numbers will be left. 2 shift means 2 numbers will be left. They become unused. So another example, 5 equivalent to 0 1 0 1. So left shift by 1 bit only. So how it is happening? 1 0 1, and finally it will be replaced by 0 only because either 1 or 0, this MSB will be left. It is unused. So last bit will be replaced by 0. So 1010 means equivalent is 10. So 5 into 2, 10. So in this way, multiplication is applicable by using the shift operation, shift left operation. That is important. And next one, the same left shift arithmetic. First one logic, second one arithmetic by 3 position. The same example, 3 we have to do 1 0 1 0 1, but this is the difference. Previously these bits are replaced by 0 in case of logical operation, but in case of arithmetic operation all 3 bits are replaced with 1, but under the condition that those who were left from the MSB either 0 or 1, no need to bother. Next, third case with the carry. So previously logic and arithmetic both the cases we have seen without carry. But with the carry, if we are using, what will happen, how to perform the operation we see here. So there are conditions to do this, to perform this. Logical shift left with the carry by 1 shift only we perform in this case. So the conditions are: number 1, MSB moved to carry. MSB moved to carry. LSB is made 0, and then remaining bits are shifted to left. So these 3 conditions are applied in the example 1011 0011, and carry is assumed to be 1. So first condition, MSB is moved to carry. So here MSB I have given the variation by color, blue color 1. This 1 is coming to carry. And second is LSB is made to 0. So these 2 conditions are satisfied here, and then we have to move the remaining bits to left. So what are the remaining? MSB already shifted, carry already okay, and then 1 1 0 0 1 1 0. That's all. So in this way we have to do. Next one, shift right. As we have done in the left shift, that same three categories we have to follow. Number one, shift right logic, shift right arithmetic, and then with carry. So number one, logical, same 3 bits position we have to change. It is used in serial bit operation. So the applications are given here: serial bit operation, arithmetic operation, remainder tracking. And in this example is given 1 0 1 1 0 1 0 1. So 3-bit position. So in the LSB position, 3 bits we have to take, and the colors are given 1 0 1 1. So remaining shift right 1 1 0 1 0. And then previously this 3-bit position shift means 3 bits should be made as 0. So in the same way, 0 0 0, 3-bit position 0 in case of MSB. In the left shift, we have to make 3 LSB bits 0. Here 3 MSB bits 0. And how it is mathematically performed. In the previous case, 5 after shift, it gave 10. Here, 10 after shift, it gives 5. So there 5 into 2, 10. Here 10 by 2, 5. So 1010, shift right by 1 bit. So here automatically 0 1 shift right. Shift right means 1 here 1 0 1, and automatically the this position will become empty. So it should be replaced by 0. So in the previous case, LSB is made 0. In this case, MSB is made 0. So 0 1 0 1, automatically it is the equivalent of 5. 5 is nothing but 10 by 2, it is equal to 5. And then second category, arithmetic shift by 3. So here, so first type 3-bit position we have to make 0. But in arithmetic 3 bits we have to make 1. That is the difference between the two. So by 3 position means 3 LSB position, it is given color 1 0 1 1. So 0 1 1 0 1. So these 3 bits are irrespective of the values of either 0 or 1 are made as 1 1 1. In logical we have to make 0 0 0. In arithmetic we have to make 1 1 1. And next one, so these two categories are used without carry, but third category with the carry we have to do. So in this case also, like previous case, we have to use the several conditions. Logical shift right with carry, 1 bit shift we are using. The first condition is LSB moved to carry. The opposite, there MSB, here LSB. And MSB is made 0. There LSB is made 0. Here MSB is made 0. Remaining bits are shifted to right. So in this example, input is 1 0 1 1 0 0 1, and to make a differentiation I have given color 1, and carry is assumed to be 1. So first condition, LSB is moved to 1. So this is moved to 1. And then MSB is made to 0. MSB is made to 0. And the remaining bits are shifted to right. 1 0 1 1 0 0 1. So in this way we have to do the operation. So up to this we have seen the shift operation. Next one, rotate. So rotation is otherwise called as circular shift. So first one, rotate left without carry. Without carry, in this case we are going to shift. We are going to rotate by 3 bit. So in the problem, the input example input is 1 0 1 1 1 0 1 0 1. So 3 bit left. So 1 0 1 I have given here. Remaining bits are shifted to left. 0 1 0 1 up to this. And what is the difference between shift, ordinary shift and rotate? In the shift operation, either right or left, the bits will be discarded. But in the rotate operation, the bits will not be discarded. It will be retained with their original position. So first one, 1 0 1, this one, and then 1, this blue 0, and then 1. Continuously coming, the order will not be changed. Continuously in order one by one, it will occupy the three position bits. Okay. So 1 0 1, like this. It is left shift without left rotate without carry. And next one, rotate left with carry. So what is the condition? MSB is moved to carry. Carry to LSB. Carry is moved to LSB. Remaining bits are shifted to left. So in this example, we are shifting left, rotating left by 1 bit only. So the example is 1 0 1 1 0 0 1 1, and assuming with the carry. So carry is assumed to be equal to 1. So first, what is the condition? MSB is moved to carry. This is MSB and it comes here, carry. And then the carry is moving to LSB. Carry 1 and it is coming here. That's all. Remaining bits, as usual, we have to shift left. 0, 1, 1, 0, 0, 1, 1. That's all. So the same left operation rotate 2 bits. So 2 bits means first 1 bit we have to do. From that second bit we have to do. So the same is carried over here. The same is carried over here. See. The same is carried over here. Next one, second shift. This one is LSB is coming to carry, and then 1 1 0 1 1 0 0. What is the condition? Okay, so here normally in the question we can ask scenario based questions. How to ask? Convert 20H to 0 to H using shift operation. How to do? How many shifts may be performed to get the solution? It is scenario based question. Okay, so we have to try. After trial we got 4, answer is 4 right shifts. So 20 it is in hexadecimal. So for 2 0 0 1 0, 0 is 4 zeros, it is equivalent to 20 hex. And then first right shift. So what you will get, it is without carry, so easy only. So 0 0 1 0 0 0 0. So right shift, so MSB is made 0. So this is the equivalent of 10 hex after shifting 1 bit, right? And then second one, 0 0 0 1 0 0 0, automatically MSB is added with 0 and it is equivalent to 0, 8 H. And then third bit. So all together 3 bits you can do, but one by one if you do, what is the equivalent we can find out. So 1 0 0 0 1 0 0. So MSB is made 0 and almost it is equivalent to 0 4 8 after shifting 3 bits, right? And then fourth one 0 0 0 0 1 0. MSB is made 0 and it is equivalent to 0 to H. So after performing 4 right shift, we can get 20 H to 0 to H. So next one, interrupt. So to avoid the processor being not performing any useful computation, a high priority hardware signal called an interrupt to the processor can do it. So suppose we cannot say unnecessary things the processor is doing. We cannot say. Sometimes any high priority operation is coming in between and we should complete that execution. That time we can interrupt, I mean abruptly stop executing the current program for the processor and make it do the important operation, that is called the interrupt. So at least one of the bus control lines called interrupt request line is usually dedicated for this purpose. So for this bus control line means it is a conducting line only through which we have to send the signal. By recognizing the signal, the processor understands that okay, interrupt occurs. And interrupt service routine for that ISR is used. Interrupt service routine usually is needed and is executed when an interrupt request is issued. On the other hand, the processor must inform the device that, so the device means input or output device, external device. Its request has been recognized so that it may move its interrupt request signal. So what is the meaning? The device which wants an operation from the processor, it has to give the ask for the request. If the request is sanctioned, then the processor will continue. If it is not sanctioned, it has to wait. That is what the meaning. If the request has been recognized so that it may move to its interrupt request signal, and an interrupt acknowledge signal serves this function. So whether it is okay or not, it depends. If it is okay, it will perform. If it is not okay, it will not perform. So for that, it is given diagrammatically. It is program 1, program 2. So in between, after performing a small operation, immediately a printout is necessary. The printer operation is needed. Then how it is happening by seeing this program? See, the program address is going on. The steps are 1, 2 up to ith instruction, I plus 1 up to m number of instructions. In between, this ith instruction is the interrupt. Interrupt occurs here because it needs the printout. So it goes to the printer program to print routine. So print routine, how to print it will be given in terms of sequence of operations, and after completing the interrupt, it is coming back to the main program. It is almost equivalent to the subroutine. In the subroutine, not a printing operation is performed, it is small task is performed coming to the main program. In the same way, after completing the print operation or whatever it may be, displaying or writing the output in the output device, whatever it may be, the operation, after completing the operation, it comes back to the main program. Transfer of control through the use of interrupts. And then, so in this case, there are two types of interrupt. Number one, hardware, and in this case also it is subdivided into external interrupt and internal interrupt. External interrupt comes from IO interrupt, IO devices. That is why it is known as IO interrupt. So in case interrupt means what will happen, only the data transfer or status transfer, power failure. So it is external disturbance only, power failure. And then hardware error, component mistakes, erratic component, data path error, control error, and timeout. Time is over, and beyond the time the operation is not yet completed, means it is the work is waste. That is why it is also assumed as interrupted. Timeout means it is also an error. And then internal comes from illegal or erroneous. So outside external devices will not make, external factors will not make interrupt. Only within the system the interrupt happens. The interrupt means it is stopping of the program also, it is known as interrupt. Error also interrupt. So internal interrupt comes from the illegal or erroneous use of an instruction or data drafts. Example, illegal opcode. Opcode is incorrect. Then automatically the function performed will become wrong, incorrect. And register overflow. So it is unable to store all the data which have been given. And then stack overflow. Formal violation. So it should not be done means it should not have been done, but it is performed or not performed. Violation of the rules, that is formal violation. And then protection violation. So for example, power failure, it is protection violation. And then hardware. In case of hardware, there are two cases, maskable, non-maskable. Maskable means it can be delayed when a much high priority interrupt has occurred. So high priority interrupt comes means it will be performed. After performing that interrupt, it will come to the main program. It will resume the previous work. So that is, the main program is delayed. That's all. It is not completely over. That is maskable. And then non-maskable. For example, normally ninth pin of the microcontroller is reset pin. If you press the button, then automatically everything will go off. In between, if it is pressed, whatever the work will not be you have done will not be saved. So that is the reset pin. So not saved means almost all gone. That is non-maskable. It cannot be retained. So cannot be delayed. If it is delayed, how long we will wait? Anyway, it will not be retained again. We will not get it back. That is non-maskable. We cannot get it back. And then second one, software. So software, a special interrupt at any point in the program, it is used by the programmer. That is the software only. So in the coding, if it is written, it is software. It is occurring by writing the code by the user or programmer. So So types normal by software instruction or execution if we get a value divided by 0. If we get a value divided by 0. So divided by 0 means almost the value should be equal to 0 by any other value if we get, then it is wrong. And that is exceptional. For that we are using some formulas in mathematics. Okay. So next one, interrupt service routine, ISR and subroutine. So already I told subroutine is otherwise called as interrupt only. Hmm. A subroutine performs a function required by the program from which it is called. So that we have already seen. ISR may not have anything in common with the program. So it is not at all related to the main program being executed at that time. The interrupt request is received. It is unrelated to the program and it is stored somewhere else. It is not linked with the main program. Whenever it is called, the control will shift to the transfer to that particular memory location. In fact, the two programs often belong to different users. Yes, maybe. Before executing the ISR, because that is why the subroutine is stored in some other memory location. So two main programs can use, because only thing the name of the subroutine is to be known. If name is known, address automatically known. It will branch. So it is possible for the two main programs to use the ISR. Before executing the ISR, any information that may be altered during the execution of that routine will be saved. The address will be saved. This information must be stored before the interrupted program is resumed. So, if it is not stored, so correct location, the control will not go. The control transfer will not occur to the correct location. It will move to the some other incorrect memory address or address step of the program. Next one, interrupt latency. So latency, already in the name itself we know it is delayed. There is interrupt latency. The processor saves only the content of the program counter. So address of the next instruction is saved by the program counter. And then any additional information that needs to be saved must be saved by the program instruction at the beginning of the ISR and restored at the end of the routine. So any additional information that is to be saved must be saved by the program instruction at the beginning and restored at the end. So restored, at the end of the restored at the end of the routine. So what is the end of the routine? Automatically RET. The delay is called interrupt latency. So the time at which it branched to the ISR and the time at which it comes out of the ISR, this time duration, difference in time, is known as interrupt delay. And then identify the interrupting devices. So which device is interrupting? Which device is asking for the service of the processor? That should be identified, recognized. How it is recognized? The simplest way to identify the interrupting device is to have the simplest way to identify the interrupting device is to have the ISR poll. So poll means it has to ask for each and every device whether you have interrupted. It has to ask poll all the IO devices, all the external peripherals. It has to ask one by one. connected to the bus. Whichever devices are connected to the bus, it will bus of the processor. It has to verify, confirm whether you have interrupted. Its main disadvantage is the time spent interrogating all the devices. It has to ask all the devices whether you have interrupted. You have interrupted. So many devices means so many times. It is asking for that. The time is getting wasted. And then vectored interrupt. So vectored already we know. Vectored means it has to go to some other place, branch. It is almost equivalent to branch. So a device requesting an interrupt may identify itself directly to the processor. So a device requesting an interrupt may identify itself directly to the processor. It has to convey its original address of what it is, and then the processor can start executing the corresponding ISR, because all the devices will have the particular location for ISRA. Suppose the input devices, so for that input output devices, some input devices have one particular location, for output devices some other particular location. In this way they have given. This is called vector interrupt. So automatically which device is interrupting, for that device corresponding address will be there. So automatically the control will branch to that location. No need to tell the address of the subroutine separately. Only thing identifying which device is interrupting. The method of so this is called the vector interrupt. So each interrupt has memory address to access, separate memory address to access. The method of pointing to this memory location is vectored interrupt mechanism. After identifying the device, it automatically going to the memory location corresponding to that device. That is the vectorium. That is the the method of pointing to this memory location is vectored interrupt mechanism, and the process of running appropriate code is ISR, interrupt service routine, and then interrupt priority. So in this case, there are so many interrupts. Number one, till now what we have seen in hardware interrupt, software interrupt, and reset. There is a high priority interrupt, low priority interrupt, moderate priority interrupt. 5 types of interrupts are there. But here, how the priorities are given, an interrupt request by higher priority should be accepted first by the processor. Whatever the work is performed by the processor, it should be stopped, and then it will start performing the start executing the high priority interrupting device, and another request from the lower priority device. Suppose the priority of the interrupts are given, okay, low priority, high priority, like that given. But second problem, at a time when two priorities are coming to the processor for execution, for response, then how it will select, which one it will select? First one, low priority interrupt occurs. Second one, high priority interrupt occurs. That time high priority only handled, okay. And second case, high priority interrupt occurs. Second one, lower priority interrupt occurs. That time also high priority interrupt will be handled. So these two are the cases. And third case, simultaneously high priority and lower priority will occur. In that case also, it will take the high priority only. So in the any time, whether it is simultaneous or not simultaneous or at different times, in between low priority will not be responded to. Only high priority interrupt will be responded by the processor. So in this case, so already we know, so for any processing of the task, any work, we need memory data only. All the data are stored in the either important data will be stored in the processor register. Otherwise, it will be stored in the external memory because we do have large quantity of memory locations. But the necessity of the data will always be frequent, but frequent okay. Obtaining the data, at what time we are obtaining, when we are in need of, when the processor needs it, immediately you should get the data. Otherwise the processor time will be wasted. It will not perform the task in correct time. It will become idle because of the unavailability of the data. For that, important access is provided, a special feature. It is known as direct memory access. So, without any interruption, without any intermediate access, the processor will directly go to the memory and take the data, required data. That is direct memory access. To transfer large block of data at high speed. So not only single one bit by one bit, no. A block of data, group of data will be together transferred from one place to another with high speed. A special control unit may be provided between an external device and the main memory without continuous intervention by the processor. So, this is the direct memory access. A control unit may be provided for the transferring of the data from the external device to and from main memory. So, two-way, bidirectional only. This approach is called direct memory access. DMA transfers are performed by the control circuit only, that is part of the I/O device interface. We refer this as DMA controller, direct memory access controller. It is under the control of the control circuit. Since it has to transfer block of data, not one by one bit data, the DMA controller must increment the memory address for successive words and keep track of the number of transfers. So, address should be tracked. Although DMA controller can transfer data without intervention by the processor, its operation will be under the control of a program executed by the processor. So, everything is under the control of the control circuit only. How much of the data should be transferred and to and from the processor, to and from the memory device, I mean external devices. So everything is under the control of control circuit.